Hello and welcome to Drugs Plus. Whether you're here for exam revision or just general interest, I hope you find this video useful. If you do, please give it a thumbs up and subscribe to support this channel so that I'm able to continue creating this content. This video is about action potentials, the impulses by which electrical signals are transmitted through the body. The cells that carry these action potentials are those of the nervous system. This is a neuron. Neurons consist of the cell body, dendrites, the axon, and the axon terminal. Impulses are received by the dendrites and then passed down the axon to the axon terminal, where it will release neurotransmitters to pass the impulse on to the next neuron. The electrical impulse, or action potential, is actually just a change in the membrane potential, or the difference in charge across the cell membrane. At rest, the inside of the cell is more negative than outside of the cell. This electrostatic gradient is primarily maintained by the sodium-potassium pump. This exchanger protein transports 2 potassium ions into the cell for every 3 sodium ions it extrudes. Many of the influxed potassium ions then flow out of the cell down the concentration gradient via potassium channels. All of this maintains the electrostatic gradient across the cell membrane, also known as the membrane potential. When an action potential is propagated, however, each part of the axon membrane becomes temporarily depolarized, meaning the inside of the cell becomes more positive than the outside. So how does this occur? The 3 ion channels responsible for this are sodium channels, voltage-gated sodium channels, and voltage-gated potassium channels. At rest, the membrane potential lies at around -70 millivolts. However, when stimulated by a stimulus, a slight sodium influx is induced, causing the membrane to depolarize. If this depolarization reaches around -55 millivolts, also known as the threshold potential, then an action potential is propagated. This action potential always occurs at the same magnitude no matter how large the stimulus is, providing it reaches the threshold potential. If it doesn't, then the resting potential will quickly be re-established and an action potential will not occur. In this way, an action potential may be described as an all or nothing event. The reason why the threshold potential is so important is because this is the voltage at which voltage-gated sodium channels open. This causes a much larger influx of sodium and the membrane potential becomes positive, as the charge inside the cell is more positive than the charge outside the cell. At around 40 millivolts, however, the voltage-gated sodium channels close and the voltage-gated potassium channels open. This causes potassium efflux down its concentration gradient, repolarizing the cell membrane. Although these channels begin to close when the membrane reaches its resting potential, they are slightly slow to do so, and so the membrane potential slightly overshoots, a phenomenon known as hyperpolarization. The sodium-potassium pumps quickly restore the membrane back to its resting potential, and the neuron is once again in its resting state. One thing to note is that during this period, the relevant section of the axon cannot propagate an action potential, as the relevant ion channels are still recovering, not having yet returned to their rested state. This is known as the refractory period and is vital as it means that impulses are unidirectional, as the section of axon behind it cannot be stimulated. So, that is how action potentials propagate. However, most peripheral neurons are myelinated, meaning their axons are surrounded by Schwann cells, which produce a myelin sheath for electrical insulation. The gaps between these sheaths are called the nodes of Ranvier, and are the only axon sections to propagate action potentials. Due to the electrical insulation, the neuronal cytoplasm conducts enough electrical charge to depolarize each node to the next. This increases the speed of the impulse greatly and is known as saltatory conduction. Thank you for watching this video. If you found it useful, please give it a thumbs up and subscribe to support this channel so I'm able to continue creating this content. I'll be back with more videos soon.